is not here, and so he asked me to then explain to him the things that you're going to explain to me today.
Sure.
But it would be great if you can record it.
Yes,
Great.
I just started the recording, and I will be able to share this link with you after we're done. Okay,
Thank
thanks.
you.
Great. Okay, so we start by adding a stream. That's what I've just done here. And you see that when you create the stream, it appears in this navigator panel. The name of the file right now is labeled document1. That, of course, can be changed once you save it. And the center part of your screen contains a grid. And a grid is where you enter the inflows of your stream and the conditions. Now, when I say inflows, what it means is this is the composition of a stream that I want to calculate the properties. Not necessarily I want to calculate the reaction of A plus B, because really what we're saying is this is what my stream contains. Tell me what the properties are. And I'll show you what the other option is when I want to react, let's say steam with rock, for example.
Right.
So I'm going to start by with the default settings, which is 1 kilogram of water inside at 25 degrees C in 1 atmosphere. That just happens to be standard conditions. Now I'm going to add calcium carbonate to the water. Okay, and I'm going to add 1 gram of it. Now what I'll do from here is just ask the software what the pH and the properties are of this solution at ambient conditions. The way I do that is to add a calculation, and there are 5 different calculations available to me, again depending upon what you're licensing. But the most common one to use is called a single point calculation. So I'm going to click on Add Calculation Single Point. When I do that, I can see that on the left side in the navigator panel, an object appears underneath that stream. And that object contains the same information I entered above. In the right-hand side, in the upper right, you'll always see what we call the calculation section. Here, for example, I've got the Calculate button, and I also have the ability to change the type of calculation that I'm performing. At this point, I simply want to perform a flash calculation at ambient conditions with this composition. So when I press the Calculate button, the software generates the model, it flashes the solution, and it tells me the properties of the phases and the distribution of the phases. Okay, that's a lot of words for simply saying, okay, I've got my results. So if I want to look at my results, yeah.
Just a question. Here you have a water that has only calcium carbonate in it.
That's right.
It's pure water with calcium carbonate. Okay.
Yeah.
Yep.
That's it. Nothing else. And notice there's no air or anything. Air would have caused the pH to be a lot lower, right? And not only that, in reservoirs where you've got 1 and 2 atmospheres partial pressure, it could be even lower. Now we'll actually do that calculation in just a minute. I'm glad you brought that up. So if we look at the report, all we're going to do is look to see the types of properties that are generated, and then we'll just scan across the values for them. So the pH of this solution is about 10. Okay. These are the thermodynamic or thermophysical properties. There's the ionic strength, very low. Here's the dielectric constant. Again, the solvency of this particular solution, which is water, and that's about pretty close to to pure water. Here's our conductivity, which is a measurable quantity, of course. You guys do it all the time. You can develop instrumentation for that. Thermal conductivity, surface tension, etc. So these are the types of data that now we're generating. Below that, you'll get your densities, your thermodynamic properties, total enthalpy of the system, the Gibbs free energy of the system. Okay, again, this may be more research-based, but nevertheless, it's available there. And the reason I'm saying more research-based is that this tool is used by a variety of industries. It could be a university, or it could be an applied technology company like Schlumberger. Actually, you got to do a lot of basic research too, or it can actually just be a plant operation. Okay, so that's why we have to provide all different types of data. Okay, coming down here real quickly, this is real important to any oil and gas operations, is what we call the scaling tendencies or the saturation of minerals. Since I added 1 gram of calcium carbonate, which makes it supersaturated, we can see that the calcite is about 1,000 times or 900 times supersaturated. But when it comes to equilibrium, the saturation value is 1. Are you familiar with the saturation, the term
Yes.
saturation? Yeah, I
Yes.
expected that. Okay, cool. You can also see that we have aragonite here, so just a different form of calcium carbonate. And of course, we can have one or the other form depending upon settings that you select. Let me stop.
And
Are there any questions
mm,
so far?
yeah, for those different calcium carbonate, I
Mhm.
mean, do you have also other? I mean, I guess for calcium carbonate, that's the only one that you're gonna take
We
into
do.
account, right?
Yeah, we don't have the vaterite, we don't have the ichthyoite, and we also don't do what you might call, let's say, magnesium substituted
Yeah.
calcium, the 1 to
Uh-huh.
4% or the 10 to 15. Now, we have dolomite in the database. In fact,
Okay.
we've got
Okay.
ordered and disordered, but
Okay.
I'll actually show that later to you, okay? I'd rather you, because that's part of a not private database, the geochemical database.
Okay.
And
Yeah.
we normally keep minerals there because they are generally kinetically slow relative to, let's say, plant precipitation minerals. Like calcite, for example, if I have magnesium in water, forgetting about the ratio for now, odds
Hmm.
are that I'll form calcite rather than dolomite. Well, not only odds, you can pretty much expect to form calcite instead of dolomite. But given time and pressure and temperature, the
Yeah.
dolomite would eventually form. Problem is, it just takes that time. So we don't necessarily keep it on unless the user knows that they have to create dolomite. Okay. Hopefully that
Okay.
makes sense to you. Okay. That I
Yes.
was being clear, rather. Okay, cool.
And so do you also, I mean, do you take into account other like specific form or crystal of calcite, like for example, oolite or these kind of things?
Oh, the oolite mineral. Okay, that's morphology, I think, right?
Yes.
Oolitic limestone and stuff. The answer to that's going to be no. We do pure mineral phases here.
Okay.
So yeah, that's a good question. That's a good challenge for us too, because really what we're getting into are the solid solutions of minerals. And
Yes.
that's a lot harder because the thermodynamic properties aren't known, let's say, for that type of, let's say, I'm not even sure, let's say what the formulation that you'd be looking at, if it would be pure calcium, calcite crystals, or, the unit cell, is it calcite or is it something else? But can I shelve that question for now? Because that's actually one I'm really interested in. I want to know how you deal with it, but it won't be something that you can do right away with the software.
Okay.
Okay.
Yeah.
But I do want to come back to that in future conversations with
Hmm.
you. Okay. With respect to what's happening in the water phase now, or even in the solid phase, we have a table called species output. And what it does is it provides you with the speciation in the solution or in the oil or in the gas um, that the software computes. So right now, we've computed that calcite crystal forms. And in the solution phase, there is a calcium carbonate ion pair, just a CaCO3 neutral species with this concentration in water. Right, here's the free calcium ion, there's the free bicarbonate, there's the free carbonate, hydroxide, etc. Okay, so that's how
Yeah.
we look at our chemistry. But that's only a piece of it. The more important piece, and I'm going to click on the customize button here, is to bring up those activity coefficients and those equilibrium constants. Okay, these
S-
things you'll know
So
about as
here,
well.
just there's nothing in the gas phase. It's because we're looking at flash data or,
That's right. We are at, so good. So I'm going to explain that. I want to bring that up now. I was saying before, right, ambient temperatures and pressures. When we look at pressure here, what we're essentially talking about is essentially a hypothetical plunger on the top of this material.
Mhm.
So if the bubble point of this doesn't, if the pressure, the vapor pressure of this does not exceed the confining pressure, there is no vapor phase. That's how we think about it. It's essentially like the first day of physical chemistry that we would have taken in university, that hypothetical plunger approach. But on the other hand, let's say, for example, I had nitrogen, right, a non-condensable gas, and I only put maybe 0.01, 10 milligrams is too little. Let's make it zero point 0.1 grams, 100 milligrams. Now press calculate. Okay. Now all of a sudden a vapor phase forms because the vapor pressure of this mixture is greater than 0.1 bar, greater than 1 bar.
Mhm.
Okay, so now I have a vapor phase. So that's the
All
way.
right.
That's OLI Sync. I guess is the best way of saying it. Okay. We use the confining pressure and the composition together to calculate the phase distribution.
All right.
Okay. Cool.
Mhm.
All right. Let me show it to you now this way. Now that we have a vapor phase present. Again, the pH changed just a little bit, probably because we removed a little bit of CO2 from the vapor phase. Let's see. Very little though. Okay.
Yeah.
But actually, it must have been another reason other than that. I'll have to look at it. Right now, I'm just going to hold off and just describe that we now have a vapor phase. It is essentially mostly nitrogen. This is the water content. And in fact, if you look at that value there, that's about 31 millibars of water, which happens to be the vapor pressure of pure water, right? So that would be
Okay.
like 100% humidity. Okay, so the concepts, in the software and what we see, in nature are still the same. This is 31 millibar of water. Once I start adding salt to this, you'll see this number go down because the vapor pressure of water starts to decrease as the salinity changes, which is essentially the boiling point rise. So all these things are essentially replicated here. Okay. Now, what I want to do in this case is the following. I'm going to start adding some CO2 to this case. Okay. Now I've already have a vapor phase present. Now what I'm going to do is just add a little bit of CO2. I'm going to add 0.1 moles of that grams of that as well. Right now that's just an arbitrary value. It has no, let's say, endpoint property. I'm not trying to define this as, let's say, atmospheric CO2. I'm just saying let's just add that much CO2 to the water at these conditions again. Now I'll press calculate. Now the pH drops to 7.25.
Yeah.
Good. And now let's take a look and see what the gas phase CO2 content is. Okay. Now I've got essentially 1.2% CO2. So we've got a much higher CO2 content, about 30 times higher than it would be in ambient air, which is about 400 ppm. And as a result of that, the temperature, the pH goes down, and the amount of calcite that precipitates decreases too.
Mhm.
Okay. Saturation drops. Remember that was about 890 before, something like that. Now it's
Yes.
766. Okay.
If you were to have several steps of CO2 injection, would you be
Mm-hmm.
able to track how much of the CO2 of which injection step ends up precipitating as calcite or other calcium carbonate minerals?
Yeah, so that would be like, let's say we're doing a CO2 flood or something like that. And
Exactly.
maybe that's even too much CO2. But the short answer to that is yes. The longer answer is probably no, because that requires a flow model. So I
Yes.
would need some sort of 1, 2, or 3D flow model attached to this. Or more
Okay.
importantly, what we would do is take something like your StimCade software, link our technology to that. You do your flow modeling there, and then OLI would be doing the flash calculations behind it.
Oh,
Okay.
okay.
And in fact, that's what we did in the early 2000s with Schlumberger in Houston. They took our model, they linked it to StimCade, not so much for CO2 flooding, but for acid stimulation. Same
Yeah.
concept, just a different acid.
Yes.
Okay, cool. But let's try that out. So what we're going to do now is, and Jordan, they've got flow sheet as well, correct?
Yes, the trial includes flow sheet as well.
Okay. So I'm going to try, and scale chem too, because I think Murtaza has scale chem.
Yes, scale chem, corrosion analyzer, stream, and flow sheet.
Okay, cool. All right, I'm going to stay in this tool just for a moment. Do I want to stay in this tool? No, I'm going to go to flow sheet. I may as well show you that pseudo 1D flow model. Okay. Now in this tool, and again, just guys, keep aware of the time, just so I don't spend too much time on one thing, and that you don't get everything you need from me in this case. What I'm going to do is I'm going to create a series of what we call separators. Okay. And each one essentially is going to represent a different section of the reservoir. Okay. And what I'm going to do is I'm going to essentially add fresh mineral to each step. So essentially, it's like we're going to flow the acid in this direction, and it's going to react with that part of the rock. I'm going to let the mineral stay present there. This may look odd to you because this isn't necessarily the way you do it, because normally what we would do is what we call a dynamic process, and we're looking at a steady state simulator, but it should still work kind of sort of the way we want it to. So let's just say that this is the sand face, okay, and this is maybe 1 meter in. Let's just say this is radial flow, right? 2 meters in. Yeah, let's make it 1.4 because I got to do it by the r squared, right? And then whatever that is, somewhere about 2 meters, let's say. Okay. Now I'm going to take my, let's take a CO2. Okay. I'm going to go create a chemistry. Let's just change this to, there's a lot of details here that I'm not explaining right now, just to show you an example.
Yeah.
Okay. Here's my calcium. Let's put quartz in there. Do I have quartz? I have to use the geochemical database. Bummer. Let's just leave that out for now. I'll add iron carbonate instead. So let's say we've got calcite and siderite cementation in this case. And then I'm going to add my CO2, okay, and some sodium chloride. Always need some sodium chloride in there. Okay. And what we're going to do now is we're going to take S1 here, which is my sand face cement, and I'm going to say that it's I'm using moles per hour. See my units here? I'm just going to change this real quickly. But I want to change it for all of it. So I'm going to just go here, change this to mass, that's all, and then press OK. Simple. Now I'm going to come back here. I'm going to say that I've got maybe 1,000 grams. Well, let's make this easier. Let's say 400 grams of water and 500 grams of calcium carbonate, 100 grams of siderite. So let's just say that's somewhere about 30% pure liquid and about 70% solids. Okay, for now, even though I'm missing the quartz on that. And then I'm going to come here. Actually, I'm going to repeat this. Control C, come to each one of these and do the same thing. Okay. Oops, there we go. And the other thing I want to do is instruct the software that we're probably in this particular zone at maybe, I don't know, maybe 120 degrees Celsius and maybe 200 bar. Okay, wouldn't that be nice to get those low pressure wells again? Okay. And just make it easy for us. I'm going to do the same thing here. Okay. 120. So hopefully as I'm doing this, you're starting to see similarities between some of your own flow models. Same sort of ideas hold, right? We define the temperature, the pressure, the flow, and then the composition. And then the software has to calculate what the properties are in that system. So now what I'll do, now that I've got my reservoir temperature and pressure defined, I'm going to now take, and I've got my solids here defined. Right? Do I have it for all of it? I do. Now I'm just going to take this fluid here, and let's say it's going to be 800 grams, let's say 500 grams of water and 500 grams of CO2. Okay. You know what I did forget to do with in my sand? I forgot to add my sodium chloride. Let's just put maybe, I got 400 there. Let's make it 40. That'll make it 10% salt. So hopefully I'm not confusing this too much since I'm doing this on the fly. And if I am, we'll stop and start over again. But really what I want to...
I'm just glad we are recording this.
Oh, yeah, not a problem. Okay, I'm going to call this my injection. Right? And I really want to just follow this injection fluid as it enters this part of the well, right? This radial zone, goes into the next radial zone. Next, essentially what you think, what I'm looking at is like I've got these little cylinders, these radial cylinders. This is the one that's closest to the well. This is the next ring out, the next ring out, and the next ring out, if you think about it like on a vertical scale. And I want to know how the chemistry is changing and how the pH changes, where my CO2 goes, all the other things, what happens as I do this. So hopefully I've got everything done right. I have no more errors present, and I'm just going to try and press calculate here. But before I do that, I'm just going to save this as SLB example. and just going to press calculate. And as it's calculating, again, what's going to happen is this injection fluid, 1,000 grams of it, is going to react with this rock here first. The liquid is allowed to move to the next step. The rock essentially, because I've got this stream here, this is the rock, that stays in place. So it's not allowed to travel along with the liquid. So what comes out here is just that 1 kilogram of water with whatever limestone and siderite it dissolved.
Mm-hmm.
That liquid then goes to the next step, and the next, and the next. So what I'm going to do now is, just to make it easier to look at, I'm going to add what's called a call out. And we're going to just show the pH progression as we go from one step to another.
Okay.
Okay. And you can see pretty much the reaction's almost is just about complete by the time we get to the second one. So very little's happening after this. Okay. But there is still a slight change. Now, to make it easier to look at or make it more relevant, I'm going to click on this once again. And I'm
There's
going to
not
look.
really a distance being taken into account. So basically, I mean, if you're far away from your starting point, or if you're close by, is not taken into account, is only a step.
That's right.
Further.
That's
Okay.
right. And that's where the dynamic simulator comes in. What we have to do here is say, okay, for the first meter from the well, I have 1,000 grams of material.
All right. Okay.
And
Yes.
and if I'm injecting at this rate, which is kind of small, then essentially this becomes my time step. If I'm injecting 1,000 grams of this injection fluid per hour, I know, and I know my porosity is, I'm sorry, my porosity is, I know how far out it goes in 5 hours or something like that.
All right.
Okay, but this is what I would call I'm trying to think of the right word, an inadequate way of actually doing what you want. It's just the only thing I could come up with in the 10 minutes that we're together right now.
Yeah. No, it's very interesting to see the kind of information we can get. Yeah.
Yeah. Now, to make this actually more interesting, what I'm going to do is I'm going to actually add that geochemical database. So now you can see things like dolomite. Okay. Although I'm really not going to do it right now, let me just at least show you. These are all the different solid phases that are either in the public database or the geochemical database. And this is only for calcium, iron, sodium, chloride, and carbonate. Okay. Once I start adding magnesium, potassium, barium, strontium, sulfate, the number of phases will start to mushroom. Okay, which is good,
Right. Yeah.
and sometimes not so good. Okay, but we want to make sure we cover everything, so we're not limiting you. Okay. Cool. Now, let me just jump back here real quick. Now that I've got my geochemical database in, I'm going to add quartz, because this is really where it gets interesting. If I go back to my flow sheet here, and I go back to my solids, I added a lot of cementation material. But now what I'm going to do is say it's got about 90% silica. So I'm going to add, let's say, I've got 500, 600 grams of rock. So I'm going to say it's 540. That's 90%. And then I'm going to make this 50 and that 10. Okay, so that's going to be essentially what my rock contains, including the connate water. Okay, I go to here. And again, forgive me if I'm playing with this. This has always been interesting to me. But now we're going to see actually what's going to happen is with the CO2, we'll dissolve all the carbonate here, and we're going to see a lower pH, and then we're going to start etching away at the carbonate here, as long as I have enough. So I'm going to make this maybe 2,000 grams. Let's recalculate. Okay, good. So now we can see a difference between here and here. And what we'll do down here is I want to see what's left of the rock. So this is the rock I added, right? Calcium carbonate and siderite. Let's see if we have any left over. Okay, we do. We still have some rock left over. We only, in fact, dissolved 3 grams and 1 gram of each. So I'd have to do a lot more injection of acid.
Right, yeah. No, it's very interesting.
Yeah. Now, before we leave this, though, let's go ahead. Let's say we don't have illite in here, but I can add kaolinite. That's always going to be interesting because now I've got aluminum and silica present. And
so here,
yeah,
I'm sorry to interrupt.
please.
So if we have, I mean, if we are in the reservoir, we also need to take into account the fact that we may have a hydrocarbon phase, and that
Yeah,
CO2 is going to be partially in the hydrocarbon phase. Not everything is going to
that's
be in the
right.
water phase.
That's right. Yep. So what we're going to do here is I added pentadecane. I'll add maybe decane and add some methane. And you know what? Pentadecane's too light rather. Let's add something like tricosane. I think that's no tricontane. I never get these things right. C30H62. What's that called? Oh, okay. Anyway, there it is. So I've got, let's say, 3 different molecular weights. Now that you're right, now it'll be a little bit cooler what we can do here. Okay. Because then what we're going to want to do is add the hydrocarbons here, right? So we can see the partitioning.
Uh-huh.
And also, once we start adding the aluminosilicates, and if we start adding some HF or nitric or some of the other acids, we can start seeing the dissolution of the aluminum, or the reaction of the aluminum with the fluoride into this system. So I'm going to leave the aluminum out right now, but I am going to put in, let's say, the hydrocarbons. And I'm going to put in 100 grams, 1,000, 100 grams of each. Okay, that'll give us a 4-phase system now. So we're going to have solid, right, from here.
Mm-hmm.
We're going to have water. We're going to have the vapor. The vapor, rather, for here, and then the organics here. And so I'm just going to copy this again to these, just so that they're the same composition. Okay, and now what we're going to do is we're just going to watch the CO2 content. So I'm going to press calculate. Better stand back just in case it decides the computer starts to smoke. Let's see. Good, all done. Okay, now I'm going to plot the, how should we do this? Maybe the partial pressure of CO2 in the vapor phase. Yeah, let's just do it that way, CO2 vapor. Yep. Okay, so this isn't exactly true to mass balance. We can see the vapor, the CO2 in the vapor phase decrease, but that's essentially because we're adding more hydrocarbon each time. But the point I wanted to get at was the one that you described, is that, yeah, you got hydrocarbon in there, the CO2 is just going to start dissolving into the hydrocarbon. And so maybe what I should do is show you the CO2 and the hydrocarbon. So I'm going to go into liquid 2 and show the CO2 in there. Okay, so we start with 230 grams there, copy, paste. Now it's 517. Now it's 673. Oops, sorry. Get this thing to move over. Paste. 860. So I'm going to shrink this again so we can see it. So we can see the progression, the regression of CO2 from the vapor, and it's partitioning to the oil phase as the result. Okay.
Yeah.
Cool.
Okay.
Yeah. The other cool thing would be, since these are usually constant volume systems, if we needed to do this at the bubble point. Okay. So we could see, for example, how the pressure increases. So we can do the bubble point pressure. Now we can see how the pressure increases as we increase the loading into this fluid. Assuming that the volume remains constant, we're injecting fluid, there should be a pressure increase. And we can either calculate that through a bubble point pressure or something called an isochoric, or a constant volume system.
Okay.
So you can, and the cool thing about that is then you get the compressibility effect on the CO2. And it'll go in, and then of course the partial pressure increases. So now what I've done is just given you kind of like a random example of what the two tools do. Which one would you like me to go to next? Or would you like us to stay with this example and go a little deeper?
No, I mean, that was really interesting for me to see it, and I'm looking forward to play with it myself. I'm only sorry that my colleagues are not here, but they will see the video. I'm sure they will be excited too.
Oh, cool. I'm going to bring up, as you're thinking, I'm just going to bring up another example because these are actually some of the ones that we've done because of Schlumberger and other clients. Like we've got a steam flooding example here. I think I've got an acid stimulation one. This is an old one. I'm not even sure if it works. Yeah, okay, I've got to get the chemistry working. So here, for example, let me just put the geochemical database in place here. Here, for example, just like before, I created the rock with feldspar and kaolinite and calcite. And then we just created a mud acid, and then we mixed it together just to see how things are going to. Just going to go change something here, just to see how things would react. Okay. And of course, what we're interested in is seeing how the aluminosilicates dissolve. I think I can just recalculate now. Can I? Nope, I just got to do it here. I had the organics. That's what you were talking about before. Yep, got to bring in the organics. Okay, now I think I could run it. Can I? Oh, still have to get rid of something else. I used to have an old database called Oil Field to do these calculations, but we're just going to use a geochem right now. But now the thing is, in this example, back in studio, so we're now back at the ranch at OLI Studio. This is a single cell. So this calculation I'm doing here represents one of these only.
Okay. All right.
It.
Okay, and those, they communicate, right? I mean, we can create all the water properties in one and
bring it to
then
the other.
use.
Sure.
Yes. Okay.
Or you can just stay here and build the water properties here.
Okay. All right.
So, and that's part of that's kind of like the there are overlaps between the two software technologies, but there's also unique differences. This tool here that I have up now looks at things at the process level, much higher than the OLI Studio. The Studio looks at things at a stream level or at, let's say, intimate mixing. You know, for example, this stream here that I'm doing, this could be essentially a pour throat. It could be as small as that or as large as a 10 cubic meter tank.
Okay.
It's size independent in that case.
All right. Okay. Another question. Is there any way to take into account potential microbial activity that may happen in the reservoir and that will contribute, I don't know, to add some CO2 or H2S, or do you have to just assume, well, we have also some CO2 coming from there and we'll just add the CO2?
I can say with great confidence, no, we cannot do that.
Okay.
But what you can try doing is the following. Because, okay, I'm just going to leave this example here, then I'll just send it over to you. Let's say, for example, this is the first case I started with. Add stream. I've got sodium sulfate. Okay, actually, maybe I should add an extra 2 there. Okay, and I'm trying to think how I could do this. So this is my sulfate in my water, and I want you to use SRBs to reduce this. So how would I reduce this? I've got to transfer. I've got to make carbon. Nope, I can't do it in this tool. The only way I can do it, I'm glad I actually thought about that first, is maybe to use it in this tool. But really what we would say is we would mechanically reduce sulfur from S+6 to S-2. And where I'm going with that is this. The software does contain redox reactions. Okay, but those redox reactions are thermodynamically driven. Whatever gives you the minimum energy. Okay. But as you know, bacteria are not driven by that, right? And as a result, oh, wait a second. So yeah, you see, I would need to, for example, oxidize carbon and reduce sulfur simultaneously in order to generate those electrons, transfer those electrons. And I'm not sure if there's a direct way of doing that. Give me some time. Next time we're together, I'll see if we can think of a kludgy way of dealing with that. Kludgy meaning what kind of workaround can we create to create those SRBs, or the reduced H2S rather.
I'm just curious. So, what's under the kinetics tab? I mean, what kind of kinetic reaction do you?
Yeah, so it's a basic module. What it is we will take. Let me just jump into here real quickly. Actually, I'm going to describe it this way first. When we did the calcite reaction before, and I was going to show you those equilibrium constants, these are the chemical reactions that are used to calculate equilibrium. And I could take any one of these chemical reactions and limit the rate of the extent of its reaction. So for example, this is the precipitation dissolution reaction of calcite. I think that's the calcite one. Yeah, there's aragonite there. What I can do in the software, and it's easier in this tool, is to take that chemical reaction. So let me go find calcite. If you see it before I do, there it is, calcite.
Yes.
And it's going to react to form, actually I'll do it this way, calcium ion. Just ignore the suffix for now. That's something we use, and I'd have to explain it to you. Okay, so there is that chemical reaction that I have just recreated from a normal equilibrium reaction. And then I've got one of two options. Actually, I have three options, but only two of them in the version I'm using. I could either use just a basic rate function that will be driven by an Arrhenius equation. Okay, so what it means is I'll take the change in calcium carbonate solid is equal to the change in this plus the change in that, and then I'll have with that here it is here. This is my rate expression. So this is the forward rate constant and the expression. Here's the reverse rate constant and the expression, and multiplied by the volume of the liquid. That gives us the mass, because this is essentially mole fraction or concentration units. So this I would then put in my pre-exponential or my activation energy values there, plus my exponent my rate order for the given reactant. Hopefully that made sense. I think you guys are much more versed in it than we are, so I'm sure it was actually kind of rudimentary. But then you can also do what's called user defined, or you can create your own reaction rate. So for example, I may define, let's say for example, K forward is, no, let me do it this way. I'm going to say that inhibitor effects is equal to maybe pH, actually H ion, times maybe PO4 ion. Okay, none of this stuff is in there, but I'm saying PO4 is like a scale inhibitor. Okay, and then I can say that ion H2 is then equal to ion H squared or something like that. And then I can write the rest of my reaction down here. But the point is, you can either do it based upon an Arrhenius type expression, or you can create your own.
All right.
And then you can say that, here the rate is equal to, oops, I did it wrong. Okay, well, let me stop there because I needed to put a few extra parameters down. But you can just enter your own kinetic data in here. We just have to provide you with the proper formatting so that you're entering it properly.
Right.
And you just saw that I didn't use the right formatting, which is why it yelled at me. So.
Okay.
So let's see. So that was like a 5-minute answer to your 30-second question about what the kinetics were. And let's see where else we can go with this that may be useful for you. Actually, I'm going to jump back into Studio for a second, and I want to show you how most oil and gas customers use the software. I'm going to bring up something called ScaleChem. This is getting into the production side of what you were describing.
Yeah, that's the tool that I was originally looking at a few years ago when I was working with the labs.
Oh, cool. Okay, good. Now, this file here, again, these files are always available to you. This file here starts with a brine analysis. Okay, this is it's decent. It's about 2 molar ionic strength, that kind of thing. Okay, it's got some radioactive scale in here. We just added this probably just for show and tell kind of thing. Okay, here's a gas analysis. Okay, and the nice thing is I got a lot of data from Core. You guys still own Core Labs, is that correct?
No, I mean, we have a rock lab that work on core samples, but Core
Oh,
Lab
I'm sorry. Yeah.
is a different company.
Oh, it is. Okay. For some reason, I thought it was Core. Then everybody that's listening to the video, sorry about that. I have received data from Schlumberger before, and generally, you guys are really good at it. You know, you'll provide the data in either mole percent, or weight percent, monophasic, biphasic. So the nice way that you guys provide the data makes it easy to enter it. In fact, I think we used your type of format when we designed these screens. Okay, I know.
All
I mean,
right.
I use that as those as examples. Um, and so you can either do biphasic, which means I'm going to enter a gas analysis here, biphasic again with the oil analysis here, or I could do monophasic with the stream object. Okay,
Okay.
cool. But now in this case, let me just go ahead and hide 0 rows. Okay, in this case, I've got an assay, a distillation curve, plus my CO2 for the oil. I've got my GC, it's a analysis for my gas. I've got my brine analysis. Now what I'm going to do is create that representative reservoir fluid. You're going to see elements of what you normally do when you look at reservoir chemistry in here. It's not a complete understanding, but it's just a basic approach. So what we do here in this, essentially this reservoir object, is we enter the production rates. So this would be the surface production rates. Here we've got the flow of brine per day, the standard gas flow per day, standard oil flow per day, based upon the analysis here.
Mm-hmm.
We've got reservoir temperature and pressure here. And then we instruct the software if there are any cementing materials or minerals that are in equilibrium with the fluid that exist in your reservoir. And what the software is going to do is it's going to actually adjust the iron, calcium, barium, sulfate, carbonate, and chloride concentrations that were given in the brine analysis so that these minerals are in equilibrium with the multi-phase fluid that exits the reservoir. So what we get from the calculation when we look at it is that the software needed to add actually quite a bit of iron and carbonate to the water, of iron and chloride to the water, substantial amount of calcium and carbonate, but only a little bit of barium and sulfate to the water, so that all three mineral phases are now in equilibrium with the water and the gas and the oil when it exits the reservoir. Okay.
Can you remind me? I mean, because I saw that before and I didn't ask, what's the difference between the pre-scale and the post-scale?
Good question. And it relates back to the kinetics you were asking us before. The pre-scale is what we all know as the scaling tendencies. This is what they base their scale
Okay.
inhibitor dosage at. This is the equilibrium state.
Okay.
I'm sorry, this is the pre-scale, right? This is the equilibrium state. And we need to show this because in some cases, certain minerals may be supersaturated, but by the time we get to equilibrium, they're subsaturated because of a competing ion effect.
Okay.
So it's still important to show both, although most customers just care about this.
Yeah.
Okay, cool. This down here becomes our new brine composition. Okay, this was the brine analysis, let's say, taken at the surface. This is the brine composition that's predicted in the reservoir. It will include the updated calcium concentration, the updated iron, if that's practical. Okay, sometimes it's unreasonable to saturate. Right? For example, the iron here is 66 mg per liter in the reservoir, but what was measured at the surface was 2. Now, the lab is not going to make that kind of mistake, so either 62 mg per liter has dropped out somewhere in the reservoir or up the well, or there is something else, or we've made a bad assumption that siderite is saturated or is a cementing mineral.
But there might be, I mean, if you take a surface sample, there might have been a lot of chemical reactions happening on the way to the surface, from the reservoir to the surface, that you can't really predict, right? I mean,
That's right, yeah.
if you've lost some material, I mean, you just don't have it anymore.
You're right, yeah. So, for example, let's say, I agree. And so we provide that as an optional calculation. It's not a requirement that you saturate. Okay, but it's there in case in case you want to test it out. Okay,
All right.
and of course that's where the geologists can come in and they say, yeah, you got siderite. So either it's unreactive or or it's saturated.
Okay.
Now coming down here, this is really the cool part that I like. Once the the brine analysis now has the dissolved organics in it as well. Okay, so we now have essentially multi-phase equilibrium among the brine, the gas, and the oil if at reservoir conditions both phases are present. But since we're above the bubble point pressure here, really all the gas is compressed into the oil phase. So we just have a monophasic hydrocarbon. Okay.
Yeah.
Right. Good. This is our dissolved CO2, which we'll use for corrosion calculations. This is your bicarbonate, etc. Okay, and then when it comes to doing a scaling calculation, there is a different object called scale scenario where we predict the scale rate, saturation ratio or scaling tendency. Again, that's the pre-scaling tendency you asked about a minute ago, from the reservoir, which starts at 1, up to the surface, depending upon the temperature and pressure along the way. Okay, and those temperatures and pressures are defined here.
All right.
Reservoir, midwell, separator. Or, and we actually do this a lot when we do halite scaling, is we create what's called a contour diagram, where we look at a range of temperatures. So if we're starting at 10 degrees Celsius, let's say it's at the seabed, that could actually be lower than 120 degrees Celsius is a high temperature, 40 to 650 bar. Okay, that means we're actually calculating about 1,400 data points, and then we're plotting whatever variable we want to. So right now I'm plotting the pH from at any temperature and pressure.
Yeah.
And what clients generally do, BP does this quite a lot with this, is then they will overlay their production profile on this, so they can see if they're in a corrosion risk area, a scaling risk area.
Yeah. Okay.
One of the things we do, I'm sorry, go ahead.
Yeah, a question, because I was still thinking about my previous question about, the fact that some species will drop out by the way they reach the surface, and what you measure does not necessarily represent the water composition at reservoir conditions, just because you don't know some of it. You don't know what's in there. I was just wondering if you ever compared actually the composition of the different fluid phases when you had, let's say, separator samples, and then you actually had access to a downhole samples that were flashed in the lab, and then all water properties were measured right at the flash moment.
Yes, that's a great question, and the answer to that is whenever we can get our hands on an MDT sample like that, we will take it, because we want to see how accurate some of these assumptions are. So that's an emphatic yes. The problem is they're so few and far between that we don't get a whole lot of them. We used to work with Oil Plus a lot because they used to get these samples, and this is like in the mid to late 2000s, and we would look at that. But I haven't seen much of that over the last, let's say, half decade. So, but that's kind of like gold if you can get that information.
Yeah.
Then we can see how well the predictions are doing.
Yeah, because we always recommend our clients basically to, even if it's just water, to still take a downhole sample to really get the information on the formation water.
Yeah.
So yeah, and they always come with, well, where we can always like predict back from a surface sample, but is it really true? It's always a big question.
That's a tough one, yeah. And when we teach this class, I would say that's probably the one that that's the question that we spend the most time discussing.
Yeah.
What do you?
I can imagine.
What's the judgment there? Yeah. And so, and anyway, so yeah, I'd like to get more. We'd like to have more knowledge there. But what we then do, though, with the software, what you can do is, in a scaling study calculation, the software gives you the flexibility to what we call drop solids, meaning that you can force iron out of solution. And with that, you can then see if the calculated surface composition matches what's measured. So here, for example, I can, let's say, drop all the solids along the way. Okay. Actually, not in the separator, because that's where, because that's where I'm sampling it. Right. If I recalculate this, then what I'll do is I'll look at the final iron concentration in the water and see if it goes back to 2 milligrams per liter. Now, I remember taking these samples, and if you let them sit for a day or so, you'll end up seeing the precipitate, at the bottom of your when you're sitting, when it sits in the lab. Do I have solids on? I do. Good. Yeah. And so it also depends upon, when you do the measurement and the brine analysis, was this from a digested sample or was it just from a filtered sample? But let's take a look at the iron concentration. Okay, so I'm just going to measure the iron concentration here. It's called material balance group totals, which is essentially the total dissolved iron. And you know what? I'll take it. The number goes down to 10 milligrams per liter. Measured at 2, but we started at 65 and it drops down to 10.
Yeah, it's pretty good. Yeah.
At least it's going in the right direction. That's what I'll give you that credit. And the other thing is, in this particular case, is this may in fact not be at ambient. It's not exposed to the air here, which means CO2 can degas and more solids can come out.
Right.
Okay, so, yeah. Okay, Jordan, I stopped there with 2 minutes left. There's so much more we can cover, especially with a company like Schlumberger. But just figure out what do we want to do next.
Yeah, so I think what we need to do is I'll send you this recording. I'll send you the files that AJ worked on. And then, as you get a chance to look at it, please reach out. So we are, just from the commercial side, we're trying to target this global license to close this at end of this month. So assuming that goes forward and everything is good, then you should have access through the next year. It will likely be a 1-year contract, but it should be, again, global access. And then, we are here to help. So as you have cases that come up, even if it doesn't work out for some reason, this global license, we're still here to help, because if you do find value in it, there will always be a way for you to get the software and for us to help. So.
Yeah, so on my side, so my first action item, let's say, will be to share with. Actually, I have one colleague, maybe two, who will be really interested in seeing this recording, and hopefully we'll have the chance to play around a little bit with the software and chat among us to really evaluate the need for our team. And maybe discuss again with you more in detail our application, what we are trying to do, so that we get also a bit more feedback on the best way to approach this. Yeah, so it's a little bit of a not so good timing, because I'm going to be on vacation next week, and one of my colleagues is also on vacation. But we should be able to get back to you the 3rd week of July or around that.
That's great. Yeah, that sounds good. Okay, so we'll plan to be in touch in a couple of weeks if we haven't heard anything. But in the meantime, I'll send you the email with the link to the recording and this case file. So, well, good. Enjoy your holiday, and thank you for joining us.
Thank you. Thank you very much.
All the best.
Bye-bye, everybody.
Bye.